Hi, I would like to talk to you about something that's near to my heart and that has come close to something else that is recently near to my heart, which is physics and machine learning. So a bit about my background. I started in physics, became a bit more mathematical physicist, did a PhD, became a data scientist, and now I work at Bowery Farming. And just a shout out, we are hiring for a machine learning engineer and a data scientist, but this talk I'm giving today is not in any way representative of what I do at Bowery Farming. So just don't let this be the pool. I am more than happy to talk about all the interesting things we do at Bowery, because it is in its own right incredibly interesting. And if you want to follow a little bit more on, if you want to have a bit more reading material after this talk, you can go to my GitHub, and I have some extra stuff there. So a bit of the. So why am I interested in this? Well, so I come from physics, many body quantum systems in particular, and I now work as a data scientist. And there's always been some input of physics and of course other disciplines into machine learning, but recently the noise has sort of amped up a little bit, and I would like to talk to you a little bit about what sort of that what that is, and what's causing that, and what this might bring for you in the future. So we know already that empirically that some deep learning protocols are really good at solving some types of problems. And you might think, well, do we need to know a bit? Do we need to study this more? We already empirically have such good results. You can try all these things, and you can just stack them all up on top of each other and get great results. But I think it does make a lot of sense to try to answer the question of why these things work. And let's just take a step back first. It is in principle seems like a really hard problem, because there's a lot of data. For example, in a classification problem of an image. So that means that there's like a huge number of probabilities. So how would a system that has to look at all these data points like learn what it is looking at? So let's take a tiny little step into mathematics. In principle, they say a neural network can approximate any smooth function, but it can be very expensive. And that's kind of where I'm going to leave it, because what we actually want to know is why neural networks that are quite small in the number of neurons can still model so many of the things that we are interested in. So one thing that's that might help us a little bit is the notion of simplicity. So what you see here is a fractal, which looks very complicated, but actually it can be generated by a relatively simple algorithm. Another example is the snowflake algorithm. You can draw snowflakes yourself very easily by starting with a triangle and then taking every edge and making a little triangle on the edge. So if you do that a few times, you end up with actually quite complex looking snowflakes. But the algorithm you used to make this was really, really simple. Another example here is where you see on the right, you see something that we actually see in nature, and on the left is an algorithm that produced that same thing. It looks very realistic. And if the point here is that if a pattern is really easy to reproduce, it is just very likely for it to happen in nature. You see more examples here. So one idea of why we might find all these simple patterns everywhere, well, if there's a low complexity, there are just so many symmetries, so many ways for the same thing to appear. So that might make it much more likely for simple things to appear. So let's pause a little bit with just a bold statement. This is, of course, not the end point of the discussion today, but I think it seems reasonable that the world has a simplicity bias. But that's not very precise. So let's put on our physicist hats for a moment and say, what other things can we learn from physics? Can we take from physics to answer our question here? So object detection, for example, another, like a very widely used, widely seen problem, has an implied scale. So in the center, you see, the object that we want to detect, a bicycle. And if you zoom in on the right, you see something that doesn't look at all like a bicycle. If you zoom in so much, you have no idea what you're looking at. And on the left, you see, well, there's actually, I promise you, a tiny bicycle there. But you wouldn't be able to tell it apart from anything else. So that's clearly not the right scale to look at. And if you were to look at similar objects like bikes or cats, you would again see, if you zoom in very much, there's no way you can tell which is which. And if you zoom out a lot, they all look the same. Physics is also something which has an implied scale. So if you see a magnet that has like a certain type of behavior at a scale that we can understand, if you were to zoom in into its constituents, you wouldn't necessarily be able to tell that that's a magnet just from looking at every single particle that makes it up. What you need to do is actually zoom out to just the right scale and to see patterns, emergent behavior that looks like the kind of behavior that you're looking for. So the way physicists do that is using what we call the renormalization group. You don't need to know what that is. I'll just tell you basically what it is. You look at a microscopic theory that describes sort of the individual particles, and then you sort of zoom out and you try to look as if through blurry glasses at the same system, and then you look at what that changes and what the new emergent behavior is at that different scale. So for example, here you would combine these individual spins into superspins, and so those are not actually particles, right? So they're quasi-particles. They don't actually exist. They're sort of the effective behavior of multiple particles at the same time. And you have a new theory in terms of those new sort of fake particles. And the step that you do is you change your parameter. Oh, there should not be a tilde at the bottom, I'm sorry. So you change your parameter in such a way that the long-range physics, sort of the things that you know should not change just because you've put on blurry glasses, that remains the same. And that gives you a new parameter that's describing all the interactions, and that basically tells you, as you start to zoom out and sort of lose all the details, what remains. So that's what it does. So the coefficients, this coefficient changes, but it changes in such a way that the macroscopic behavior of the system does not, because things don't just like start falling sideways just because you're zooming out. Physics has to remain the same. So we can keep doing that multiple times, and what we get is sort of a succession of different sets of parameters that are describing the physics at different length scales. And you can look at all those parameters. They can be very high dimensional because basically every single one of these ij's is basically could be a really long vector of all the different forces that are present in your system. So let's say, for example, we have this like little square letters, and it has one force in one direction, one force on like even rows in one direction, and then another on the odd rows. You want to have it like a little bit interesting, to have like three different types of forces. So let's map out, that means we have three parameters, and we start on one point in that parameter space. And after a whole succession of these like zoom out renormalization group steps, we have ended up somewhere else in that parameter space. So what we can see from here is if we zoom out and some parameter becomes a little bit bigger, so you can see in the JA direction, it became a little bit bigger, we call that a relevant parameter. So basically that parameter is for some kind of force or interaction. That interaction is relevant at the long scale because it'll grow. If it's smaller, like the B one, it's irrelevant. So basically this is a feature of the really small scale behavior that is not, that just washes away at the large scale. And then we have another relevant parameter because C became a bit bigger. So what's important is this is, to use a machine learning term, unsupervised. You don't tell nature how to behave. You just say, all right, the way I do this is preserving the long-range behavior because I know that putting on blurry glasses should not make things behave wildly differently. So in deep learning, this is actually not a new result at all, but this was quite a big result when it came out. You can actually use the same kind of technique. They call it a restricted Boltzmann machine, where you have a visible layer, which would be, let's say, your real spins. You have your hidden layer, which are sort of your quasi-particles. And if this hidden layer is smaller, then this is a way for you to zoom out, right, to reduce the complexity of your description. And you do the same thing. You try to train that in a way that sort of macroscopic properties don't change too much. They always change a little, but you try to minimize that change. So you can use those by like stacking them on top of each other. I guess most people probably have seen this. And if you encode this and decode this, you'll see that you end up with a slightly blurry version of your original picture. So the takeaway here is that what physics teaches us is we have descriptions at different scales, relevant fields, irrelevant fields, and RG steps. And those in machine learning would correspond to features, noise, and compression, respectively. So one thing that this can also kind of help us kind of answer, why do physical theories look so simple? So if you look at renormalization, this is something I'm not going to prove because it's not simple at all. But it turns out that very complicated terms that involve a lot of different particles interacting with each other have the tendency to become more irrelevant. So in physics, there's a tendency for simplicity there. And the suspicion would be that maybe in machine learning or like in the real world, let's say, things that we care about tend to have that same property. That's not very exact. I mean, yeah, what does that buy us, right? This doesn't tell us like why theories learn so well, etc. So we want to have something more tangible. So let's move to something tangible, convolutional neural networks. These are extremely successful at modeling image data. So let's look a little bit, I'll go over it really fast. So let's say you have some stack of images, and every image like the pixels of those images can take different values. Let's say maybe like RGB or something, like different colors. So you have your image data as a multi-dimensional array. So you have, all the spatial pixels, and then you have also all the values that those pixels can take. And the important thing here is that we don't, like in a normal neural network, immediately roll out all the values as one big vector. We want to sort of conserve the spatial information of what is near each other. So this is what one of those whole networks looks like. You start with your input, you do a convolution, which I'll explain, pooling, which is basically reducing your number of degrees of freedom, and you can do that many times, and at some point, all the way at the end, you do flatten it out like a normal neural network. They call it the fully connected layer, and that's where you learn your, actually try to learn your target. So let's go over it a little bit. I'm assuming most people have seen it, but why not? It's useful to have it sort of fresh in our minds. So we have this input layer. D would be the sort of the dimension of the pixels, the number of values that can take, has a height and a width, and what we use is a kernel or a filter. It's the same thing, just different names, which is smaller, but it has the same number of dimensions. So the way we do this, we have multiple of these filters. We can have one or more, whatever we want. And we start with a field of vision. We start by taking a localized part of our image. So that's where the sort of the locality of our input pixels comes into play. And we take the inner product. And after that, some activation function. ReLU is a very popular one. It's nonlinear. It learns very fast. You need something nonlinear. And basically, you move your field of vision. So every one of those convolutional operators is basically you have your chunk of input data, you have your filter. It sort of goes through that filter, and you get like one pixel value, one node value. So you move through it. So there's a parameter. It's like the stride. So how fast it moves through it. Like how many does it like center over every pixel or not? If you don't, then of course you reduce your parameter space a bit more quickly. And you go over the end. Maybe you apply another filter. Maybe you apply many of them. So the number of filters that you apply determines the dimension of your second data layer, let's say. So you've ended up with probably a smaller number of let's say quasi-pixels in your second second data set, but it may not be drastically less. And you can have a different number of filters. It can be more or less, whatever. So after that, if you want to reduce the complexity or you want to reduce sort of the number of parameters, then you can do pooling, which is you take each of these blocks and you just map them to one pixel. You can do that maybe average, max pooling. Max pooling is very popular. I'm not really going to go much into that, but that's really a quick way of drastically reducing your size. If you do max pooling, the nice thing is you can just, if you remember like which index was the maximum one, then you only need to backpropagate through those maximum sort of channels, so that's nice. So this is ReLU, and max pooling is sort of a very, very popular standard convolutional network. So the activation function is nonlinear, so basically the transformation you do on your nodes after your convolution is nonlinear, and you use max pooling. Another type of network that is not as well known, quite promising, but for our purposes much more useful, is the convolutional arithmetic circuit. So the activations are linear, and the way it's nonlinear is through product pooling. So instead of taking the max or taking the average, it takes the product of all the nodes in the pooling step. So this brings us to tensor networks. So this is kind of a sidestep I'm going to take. I'm going to first go over a little bit of like very, very basics, not really tensor algebra, but like something similar, just for you to like follow along a little bit with that. So you can think of a tensor as a multi-dimensional array. It can be, you can represent a tensor by a multi-dimensional array. It's not exactly the same thing, but I guess multi-dimensional array flow doesn't sound like as catchy as tensor flow, so let's just use the word tensor. A scalar is a tensor of degree 0. You can have a vector which has like one dangling edge. That's how I'll use the notation, or one index. If you see the bottom, that's how I would use it in an equation. Matrix will have two dangling edges or two indices, and each of those indices will have some kind of dimension, right? Like the number of values it can take. Or you can have like a degree n tensor where you see like a whole number of these dangling edges. And most of these things you don't really need to know, but just to give you an idea, a dot product between two vectors, you can write it, of course, as in the right, but you can also write it in this pictorial representation as the two dangling edges of a vector connecting together, being summed over. Sort of a closed edge basically means you're summing over that. And you get a scalar out. And you can do a matrix product with a vector, of course, and a matrix trace also leaves you with a scalar. There's also the opposite, where you, for example, create a matrix out of two vectors by taking a tensor product. You don't really need to know much about that. Or you can do something like SVD, where you split a matrix into multiple constituents. And the nice thing here is with SVD, you can do it exact, but you can also start dropping out some of the smaller singular values and sort of get an approximate value of your matrix that way. That's something that could be useful later, that idea that you can get maybe not an exact representation by splitting it, but maybe you can get an approximate representation by reducing the dimension of the bonds, the closed bonds in between. So let's go back to our convolutional layer and try to view that as a tensor operator. So we have our field of vision, we have all those filters that we want to apply to them. So let's start with the first filter. So what we've done is we've taken that field of vision and we've taken that filter. Now we unroll it into a vector and take a dot product. So we end up here with just one node. And we do that with all the other filters. We end up with an array of them. So let's just say that this is a matrix of those filters. And then we take a product between our input vector and that matrix. And let's do that for all the fields of vision we have. So these the x's are basically all the fields of vision that we could possibly have as we are moving over our image. So those are all the environments, like the little patches. So one thing to note is that after this operation, so this takes basically our number of values that our pixels could have, and it took a dot product. So basically we don't have that dimension anymore, but it does it like d prime times. It does it the number of filters times. So you're changing your dimension from d to d prime here. So in the pooling layer, remember, we just took a max or an average or something of those, or a product of all the input pixels. So you can take any number of them. Here I just took 2, but it could be more. So you have, I'm calling this a triangle just to make it visually sort of more different from the other nodes. So you can take any number of nodes and you do your pooling operator and you get one node out. And important to note here is that here the dimension actually doesn't change. So this pooling happens layer by layer. So every filter that you have, or let's say every color or whatever, you do a separate pooling step for that. So that actually doesn't change. So let's put it together. There are many ways that you can build the convolutional arithmetic circuit as a tensor network. This is a very deep way. You could make it very shallow, basically have only one convolutional layer and then have basically everything collect in one big pooling layer. You just take big product of everything. That would be a shallow network and probably not very good for learning. So, but what, so let's look a little bit at the elements here. So on the bottom, you'll see the input regions. And the other round bits, those are the convolutional weights. Then we have all this, the triangles are all the pooling, all the pooling steps. And then all those little these are the bond dimensions. So what we can use this for, so I haven't basically proved to you that this is actually a tensor network. The paper below there does do the proof. It would be probably a little bit too long to try that here. But what this buys us, that you can view this as a tensor network, is that a tensor network is actually something from physics. If we have all these little particles that have like some number of states that they can be in, and we want to describe how a collection of them behave. Normally, you can't view them as independent particles. So if the right-hand side were true, that would basically be they're sort of a product of each other. They're independent. But in reality, normally that isn't the case. So normally you have just some really big, complicated function of all of them, and you cannot really solve them separately. So the way in physics that is dealt with is, well, one way is using tensor networks, where the choice of the tensor network is sort of tries to use information about entanglement between these particles. Because entanglement is, in a way, how much it is not true, how much this equation is not true, how much it's not sort of independent, how much they are not independent particles. So depending on how much entangled they are and whether different regions are entangled with each other or not, you would choose a different tensor network. And this we can. This is exactly the same if we can view our convolutional circuit as a tensor network. We can use sort of this same kind of reasoning about entanglement. In particular, we will say, for example, if we split our image into two input regions like this, the blue and the orange part, we can choose and try to choose a network that would handle, let's say, entanglement between that well. And basically the way you do that is by looking at the smallest bond dimension, the smallest number of collection of bonds that you would have to cut in order to make them disconnected from each other. And that's basically your bottleneck. That's your bottleneck of how well you can measure entanglement between the two. Those papers below tell you how and why. So I would definitely recommend you look into that if you find it interesting. Similarly, you could look at different entanglement patterns. Maybe you're interested in how local regions are, how local regions can be modeled if they're correlated with each other. And then you would look at a smaller, a different cut that you would have to make. So that was it. Thank you. There's a GitHub page with a little bit of sort of popular science, but also other reading about all the things that I've talked about. There's a few things that I didn't cover that I'm linking to there as well. There is a Python library, actually, that you can use. It's called Tensor, I think just Tensor Network. It's built on top of TensorFlow. So I would definitely recommend play around with that. And I'll take any questions.
Questions? Hi. So I wonder, what's the use case of the tensor network in your company?
None. Yeah, sorry. So we do computer vision. I do not personally. We have computer vision engineers. We use out-of-the-box models, and yeah. So at our current company, we do not work in this at all. This is weekend work. I don't have a life.
Most importantly, does your farm grow that fractal broccoli?
We definitely should. So yeah, we definitely should. We're currently we're quite young. When I joined, our farm was still literally under construction with software engineers in like hard hats. We are working on fruiting crops now, but I think fractals is an underserved market. I agree.
On a more serious note, I've heard those who said, "Oh, our deep neural networks are problem solved. We just gotta keep feeding it more data." So right now, the self-driving car does know what to do if someone's trying to land a plane on the highway. But just give it a couple examples of that, and we'll be good to go. And others that said that fundamentally, this problem is too hard for the state of the art right now. Any thoughts from the physics perspective? What kinds of problems are set for this, and what aren't?
That's an excellent question. So I mean, the problems that are already solved, they're already solved because you already have like a pretty good intuition about it. So the sort of the tinkerers already got really far with that. With other things, well, you could say things that are currently not widely studied, but where you might have an intuition where sort of correlations between regions or between areas might make sense. But I think in those cases, you probably would already map it to something you already know, right? So you probably, a lot of things, like sound analysis, you can map that to an image and sort of solve that. So given that I don't spend my days working on deep learning problems, I don't have a great answer for you there. But I think most of the problems where it would be directly, where this sort of knowledge would be useful would probably be something that you can map to something you understand better, I should imagine.
I think we have time for one more question right here.
Can you go into a little more depth on sort of the connection you were making to like the renormalization group? So like I don't have a great understanding of what it is, but I imagine it as some sort of like tensor quantities whose like the transformation laws that sort of define a tensor will allow it to sort of like encode things about like varying scales and something like that, or something like that. So like, can you just go say a little bit more about sort of the nature of that connection with the renormalization group?
I see, yeah. So the parallel is that in the renormalization group, what you try to minimize is between two descriptions, the difference in free energy of those descriptions. And in case of machine learning, it would be something equivalent, the Kullback-Leibler divergence. So you're in a sense you're trying to find a more coarse-grained description that satisfies something that you want to keep constant, as constant as you can, which would be something that gives you like macroscopic properties of your system. Not really sure if I answered your question there.
Yeah, that helps.
Okay. Yeah, so that was that's why I stressed it's unsupervised, right? So basically, in physics, you say, well, physics doesn't change, right? Macroscopic, like a magnet is not suddenly not a magnet anymore just because you're putting on blurry glasses. But you have something similar in machine learning, where you say sort of, yeah.
Great. Let's thank our speaker one more time.